All right, welcome to section 3.2 where we're going to expand our knowledge on quadratic formulas. We saw this a little bit in chapter 1, and so we are going to move into this extending also what we just did in section 3.1 with some of that in behavior and powers and such of what the nature of the quadratic function looks like depending on the powers. So, quadratic function, which also is signified by or known as a parabola, takes on the form f of x equals a times x minus h squared plus k. So that prefix quad might throw you off a little bit. Think it has something to do with a 4, but it actually does not. It is a power of 2. Now, we are going to designate hk as the vertex of our quadratic function, and basically that's just the turnaround point of that parabola. So a parabola looks like this. The vertex is this guy down here, that is hk. Okay? We first want to locate that vertex, and then we're going to find f of x by using find a by using the vertex and another point, or by analyzing points is what we're going to do in order to write the equation of a quadratic function. Now, we are going to remind ourselves what that function was. Just the most basic parent function was that f of x equals x squared. Now, we did this always by a t-chart, and the common numbers, if you put 0 in, square it, you get 0. 1 squared is 1. 2 squared is 4. This was kind of our common chart that when we were using those transformations to determine the graph, we always had that symmetry going on where the y-axis is symmetric to, or symmetric within this function. Therefore, once I have 1, 1, also negative 1, 1 is a point. 2, 4, also negative 2, 4 is a point. So, what we have written up above, that f of x equals a times x minus h squared plus k. That's what they refer to as the transformation form. This book normally talks about the vertex form. So if they ask you to put something in vertex form, this is the form that we want. But there is another form that for quadratics we use quite often. That is what we refer to as the standard form. And that is the f of x equals ax squared plus bx plus c. So what we're actually also going to be able to do is to eventually kind of take that standard form into a vertex form that can make it very nice to graph. So let's do a couple examples here of being able to take a parabola, write the equation of that quadratic function in vectored form. So we're going to use this, vertex form, excuse me. We're going to write it in this. And then we're going to expand that formula into standard form. And actually, I'm just going to do that on the last one because I'm not sure too many of your problems ask you to do that. So we're just going to see that standard form in the last example here on the front page. So first thing that we need to do, notice here, what did I say? We need to locate our vertex. So, in this graph, the turnaround point for this parabola is this guy right here. And so, from the origin, that would be negative 2, negative 3. That is my vertex. So, I can, at this point, know that f of x is equal to a. If I do x minus the h, so if I do x minus a negative 2 becomes a plus 2 squared, plus k, so plus a negative 3 gives me a minus 3. So that's as much as I can do at this point. Now, we have to determine a, and there's two ways to do that. Up here, I told you to find a by using the vertex and another point, or by analyzing points using this t-table. So, I'm going to kind of do it both ways here so you can see both ways. If I analyze the t-table, notice this is the original, and we have to determine what we have done to kind of get this pattern of these points over here. Now, if I, from my vertex, and I go over 1, normally we go up 1 full box. Now, this one is below there. Now, it looks like it's at a half. But do I really know that it is at a half? No, we're approximating. So if I go over 2 and up 2, over 2, and instead of going up 4, now I've actually gone up 2. That kind of gives me an indication that maybe it is half when I went over 1 and up 1, because what do I do to 4 to get 2? Well, I can either divide by 2 or I can multiply by a half. So if I multiply by a half here, which is the A, that would give me a 2. If I multiply this by a half, that would give me a half, and of course this stays at 0. So does that jive with my graph? Over 1, up a half? Yes, that does jive. Over 2, up 2, that gives me a point. So sure, it should be a 1/2. So what I could do now is plug that 1/2 in for A, 1/2 x plus 2 quantity squared minus 3, and this is my function of that parabola. Now, if you're not sure about that, or if things don't line up really nicely on that t-table, then you can always use this generic function that we just did and another point. That's what this first part is here. It says find A by using the vertex and another point on that parabola. So we go down here and we say, okay, well, there's my vertex. Here's another point. There's another point. I like to use this one just because I have 0 as one of those numbers. So remember, this is my x, this is my y, this technically is y. I would be able to plug in x and y here, leaving me with an a that I can solve. So let's do that. Let's plug -1 in here, equals a times throw x in here, so that's a 0, plus 2 squared and a minus 3. So here we have an equation with one letter that we can solve. We're going to simplify this first as 0 plus 2 squared. So 0 plus 2 is 2, squared is 4. So I actually get -1 equals 4a, minus 3. And now I have a two-step equation that I can solve. So if I add 3 to both sides, I end up with 2 equals 4a. And to get a by itself, I have to divide by the number next to the letter. And when I do divide that, I get 2/4, which is the same as 1/2. And that is exactly what I have there. So some of you will be able to use the t-table and be able to do that. Others of you may prefer to use the equation. It is perfectly okay, whichever way that you decide to do that. So let's try another one. Let's first write the equation, kind of identifying that vertex there at 2, 7. Now notice, this one now is going down. So what should we know about A? A in this case is going to be negative. Here, A was going, or the parabola was going up. So it is actually A being a positive, jives with that. Same way with this one down here. It'll be positive. This one's going to be negative. Now let's do this by a table. See if we can do that table, then I'll do the equation on this third one. 0, 0, 1, 1, 2, 4. That's the original table that we have on that. And let's see what we can do to determine where did I go in the y value for this function. So from the vertex, I went over 1 and down 2 to get to my next point, 1 unit over. That is down 2. So how do I get to a -2 here? Well, I've multiplied 1 by -2 to get -2. So if that works, I would have to multiply this by -2 and get -8. Now let's verify that by going over 2 and down. 1, 2, 3, 4, 5, 6, 7, 8. And it does work. Therefore, that a value here is -2. So you can kind of get that a lot of times from going over 1 and down or up however many. It's just real confusing here when you get a fraction value because you're not always for certain, okay? So what is the final answer? Using my vertex of 2, 7 and my a, our final equation would be f of x equals my a times x minus the x value, which is 2, quantity squared, plus k, and k is 7 here. So we would do our plus 7. And this would be our final answer for that. Okay? All right, let's do it one more time with the equation. And this time on this one, we're going to go ahead and expand it down to standard form, that ax squared plus bx plus c, where I don't have any parentheses. So I'm going to identify my vertex. It's this guy right here at 2, -1. I'm going to write that function generically as my a times x minus the x value, or the h, squared, plus k, so plus a negative 1, gives me a minus 1. And now I'm going to find another point on my graph. You can choose all kinds. You can choose this one. You can choose that one. Come on this side. You can choose that one. Oh my goodness, I think I'm going to choose the origin. Why? Because 0 is nice to be able to plug those things in. So if I have a y value of 0 and an x value of 0, I should be able to now go ahead and find a. So let's do that. 0 equals, now what is this? 0 minus 2 is negative 2 squared is a 4. A minus 1. And again, just like last time up here, I'm 2 steps away. By adding 1 to both sides, 1 equals 4a, and dividing by the number next to the letter gives me a to equal 1 over 4. So that is my a value that I could go right back up here and plug in and get the vertex form if that is what is requested. But if we now need to do the standard form, we need to expand that a little bit further. So this is going to be one answer. This is our vertex form. The other one is going to be our standard form, okay? So how do we do that? I now need to get rid of those parentheses. So if you are a good FOILer and not need the FOIL to be able to do that, then you don't have to write this out twice if you know a pattern of that. Most of you probably will have to do the pattern or do the FOIL. So I'm just writing this set of quantity squared into 2 sets of parentheses because that's what my exponent means to do. And now I'm going to do my first. X times x is x squared. Outer, x times a negative 2 is a minus 2x. Inner, negative 2 times x is another minus 2x. And my last, negative 2 times negative 2 is a positive 4. Don't forget this minus 1 at the end. Now, we can actually combine like terms, and I would recommend that you do that. So, when I do that, negative 2x minus 2x is a minus 4x. Then I have my plus 4 minus 1. Now, again, I need to get rid of all these parentheses, so I need to actually now distribute the 1/4. So 1/4 times x squared is just 1/4 x squared minus a 1/4 of 4. Multiplying by a 1/4 is the same as dividing by 4. So 4 divided by 4 is 1, or 1/4 times 4 is a 1x. I'm not going to write the 1. And 1/4 of 4, again, is a 1. This time with the constant, I will write the constant. And then we have a minus 1 at the end. Don't forget that. And we're 1 step away because now these two constants actually cancel out, leaving me with a standard form here of 1/4 x squared minus x. And that would be my final answer in standard form. And if you notice in this case, the c value is negative, or the c value, excuse me, is non-existent, and it is understood to be 0 there. Okay? All right. Let's move forth a little bit and talk about intercepts and be able to also use a process in which we call completing the square in order to find that vertex form. So that's what page 2 is devoted to. So when we're solving equations like this, so in our factoring section that we did, we ended up having an equation that looks like that. Notice that it is completely factored. We have powers of 1. And so we were finding solutions to the equation. What made this equal to 0 was negative 3. What made that equal to 0 was a positive 1. So not only are they what we call solutions to that equation, you're actually visually and graphically finding the x-intercepts of that parabola. So for our equation above, x plus 3 times an x minus 1 equal to 0, we end up having negative 3 and 1. Those are our x-intercepts for our parabola. So that means that we're crossing at negative 3 and positive 1. Now notice the a value out front is positive. There's no negative out front. So we are going to have a parabola that does something like that. And that, again, is just a nice little sketch. I don't know how far down that it goes. I would have to investigate a little bit further by plugging some values in, namely -1, to figure out where it would lie, and that would give me my vertex. So, what if we ask to write an equation of a quadratic function that opens upward? So if we open upward, remember A is positive. It has a standard stretch. That means that our A value is equal to 1. We don't do anything. Remember, 1/2 kind of widens it out. Number that is bigger than 1, we make it skinnier. And we have x-intercepts of 2, 0, and -1, 0. Now, this isn't an ordered paired form. This, we are just saying where those x-intercepts are. So, in a sense, we're going backwards. So if I have 2 and -1 now, we have to think about what do I have to have in my binomials in order to make 2 and -1 roots. So what has to be inside each one of these? So I need x minus or plus what to give me 2 as an answer that kicks out? Well, here I have x minus 1 and a positive 1 is the answer. X plus 3 and a -3 is the answer. So if 2 is my answer, then it had to be an x minus 2 inside there because 2 minus 2 is 0. If I have -1 as a root, that means I needed an x plus 1 inside that function in order for that to give us a root. Now, A is positive and A is equal to 1. You can go ahead and put that out front if you want. But here, we now have our function. So what we're looking at here, this is another way to keep your answer. This is what we call the factored form. And it is like f of x is equal to a, and then we have just like a set of parentheses. It could be, in this case with quadratic or with parabolas, that we just actually have 2. So I'm going to actually take that one off. But when we get to higher powers in the next section, that means that we could have multiple sets of parentheses there to signify what intercepts that we have for that function. So let's do this next one. We have the same intercept, so that means I still need an x minus 2, and I still need that x plus 1, but now it opens downward, and we vertically stretched it by a multiple of 2. So what does that mean? Well, the 2 is my A. But if it goes downward this time, that means I got a parabola that does this. What do I need to add here in order for that to occur? I need a negative. So for my function in this example, I need to throw that -2 out front along with that x minus 2 and x plus 1 to account for all of those different pieces. Okay? All right, very good. Now, we will get into a process that we call completing the square. This is so important, not only for parabolas, but also for other conic sections like circles and hyperbolas and stuff. This will allow you to identify the vertex of a quadratic function as well as other pieces of the function. So, completing the square is used to turn a function into the vertex form, which if you recall, that is the A times x minus h squared plus k. It will allow us to find the vertex for that parabola. So here are the steps that we're going to use in order to get our completing the square done. We are going to be given a function of the form, which is standard form, f of x equals ax squared plus bx plus c. So if we're given it to us in that form, that's good. Or we can have y equals, remember that's the same. We have to look at that a value. If a is not equal to 1, a being the number in front of the x squared. See, here's a 1, here's a 1, but notice down here, we don't have a 1. So if a is not equal to 1, then factor that number out of the x squared and the x terms of the equation. We want to then separate the first and second terms, which is the x squared and the x, because we want to make sure that it is all in descending form. So x squared, x to the first, no x's. So when we separate the first and second terms from the constant, which is the number in the back, and we want to prep for completing the square. That's what we're going to do in the second step. Here's the most important one. This is how we get to complete the square. We're going to take half of our linear term, which is the x term, and add the square of that to both sides. Oops, sorry, I shouldn't say that. We're not doing it to both sides this time. Add the square of that number to the first two terms, and then if I add something on one side of the equation and do something on the same side, then I have to subtract that to make it balanced, to keep it balanced, to keep it, in a sense, we're just adding a number, subtracting it off, so technically that's 0. We're just changing the way it looks when we do that. And the last thing is to factor the first three terms into a quantity squared, then simplify the constants. And once we do that, we're going to get right back up here. Okay? Now, bear with me for a minute. I want to kind of give you that idea of that completing the square. So, if I had x squared plus 6x plus 9, and I ask you to factor that, okay? When we factored this, I did it by trial and error, but there is a special case called the perfect squares trinomial. Just doing it like we've done before. If the last sign is a plus, they have the same that match the first. I'm going to split my x squared as x and x. And what do we multiply to get 9 that we add to get 6? Well, I hope you're screaming at me 3 and 3 because that is correct. Outside is 3x, inside is 3x, gives me that 6x. So what we have here is a quantity squared, x plus 3 squared. So what we are going to force with completing the square is that we guarantee a trinomial that I can factor into a quantity squared. So not all the time does that happen, but we can do that to get the form that we want. So here we go. Let's do it on these two. We have complete the square and identify the item. So in this first one, we just need to identify the vertex, okay? All right, so first thing that we're going to do, check A. Is A 1? Yes, we can move to step 2. We are going to separate these first two terms from our constant and prep for completing this square. What do I mean by that? Well, we're going to prep for what comes next, okay? Because we have to add something to both sides and square it, okay? So I'm adding this prep in right behind here, but I'm going to bring down my 10. But if I add this piece on this side of the equation, to keep it balanced, I have to subtract that piece also. Remember, this minus this is going to give me 0, which gives me back what I started with. But we're going to change the form of the way it looks, and that's what helps us do that. That's what's really nice about this process. All right, so we've separated the first two terms, prepped for my completing the square, kept the constant, and subtracted that square here at the end. So here's our most important step. We're going to take half of the x term and add the square of that and subtract the square of that from the same side. So here's my linear term. I don't care about the x, I don't care about the sign, because anytime I square a number, I get positive. So I'm just going to take half of the number, which is 3. That needs to be placed in both of those pieces. Now, what I have forced this to be is a quantity squared, and we just actually looked at that example. I didn't even know it was the same one. X squared plus 6x plus 9. Remember, that went down to what? It went down to that x plus 3 squared. It will do that every single time on the completing the square, and here's the pattern. Once you have this piece, we are forcing it to be a quantity squared, so y equals that. We are going to take 1x. We are going to take one of these. That's why I write it as 3 squared and not as 9. And I'm going to take the first sign as a plus. And these three terms will always factor like that with that pattern. Once I've established this, now we get to clean this up. So I get 10 minus 3 squared, which that is 9. So 10 minus 9 is a plus 1. And this piece right here is my vertex form that I can now find my vertex. Now remember, finding the vertex, when it's grouped inside here with the x's in a set of parentheses, I have to take the opposite of what my eyes are looking at. So take the opposite of a plus 3. In the vertex, I have an x value of negative 3. Then we're going to take this sign as is, which gives me a positive 1. So negative 3, 1 is my answer there for that vertex. Now let's try the next one. Okay, same idea. We are going to separate the x squared and the x term because A is not equal to 1 here, or A is equal to 1 here, excuse me. So I don't have to do anything fancy with that. I'm going to separate those and then also prep for my completing the square. So I have to add something squared. I'm going to bring my 13 down, but if I added this square, I have to subtract that off again. And this is what we're going to factor into a quantity squared, and then we're going to clean that up at the end. Now, what goes inside that parenthesis? We have to take half of the middle term. Again, don't care about the negative because anytime you square something, it will be positive. Just look at the number. Half of 8 is 4. So that is what goes in each of those sets of parentheses. And once we do that, now this factors into this binomial squared. So I'm going to take 1x. I'm going to take the number inside there, which is 4. And I'm going to take that first sign, which is a minus. And then I get to clean this piece up back here. So I get a 13 minus a 16, which gives me a negative 3. And this is the equation that I want in vertex form. And what is the vertex at that point? Take the opposite of what you see with the x and the same sign as is. Therefore, 4, negative 3 would be our vertex for that function. Okay? All right, very good. Here we've got a couple things that we have to do: a factored form, vertex form, and then find all these other pieces. So let's just start with the factored form. That means I have to factor this equation, okay? Factored form. All right, so if I'm going to factor, so from our factoring section we said we'll take out any common terms first. Notice there's a 2, and a 2 in common. So if I take out a 2, I'm left with x squared plus 6x plus 5. And because I have a square here, I have to determine, can I go further with that? With a trinomial, that should factor into 2 binomials. Last sign is a plus. They are the same that match the first. Split your x squared up as x and x. And what do we multiply to get 5 that I add to get 6? Well, 5 is prime. So it better be a 5 and a 1. Therefore, that is my factored form. I now have my factors, or my powers of 1, and we are good. Now, why is this so important? That is so important because you are able to very nicely find the x-intercepts from that, okay? From the factored form, we are going to find our x-intercepts. Well, what do we need? For our x-intercepts, we let y equal 0. So there's my y value. So I would say, okay, 0 equals 2 times x plus 5 times an x plus 1. And this is where we go down the line to figure out what makes this 0, what makes that 0, what makes that 0. Now, is 2 ever going to equal 0? The answer is no. That's not going to kick out an x-intercept. But what number plus 5 is 0? And that would be negative 5. What number plus 1 is 0? And that would be negative 1. Now, you'll have to kind of watch the way that the program asks you for the answer. So they may ask you to answer it as negative 5 and 1, as what those are. But if it asks you for points, please make sure that you do it as ordered pairs. X is negative 5, negative 1, and the y values are 0 when you're finding x-intercepts. Okay? So the factor form leads very nicely for you to do the x-intercepts. Now, the vertex form is going to lead us very nicely to finding that vertex. So let's do that. This time, we have to do it completing the square where there is a 2 in front that we have to get factored out, okay? All right, so I'm going to kind of do this down here so I have a little bit of space. So for the vertex form, by completing the square, a is not equal to 1 this time. So it says if a is not equal to 1, then you need to factor that away from the first 2 terms. Not all of them, just the first 2. So I end up getting, take away 2 from each of those, and then I have to do my plus 10, so I'm doing my plus 10 at the end. Now, the difference is I have to account for this 2 when I add in something squared to that. Now, it's just like before. If I were to cover up this 2, this is just like before. Taking half of 6 gives me a 3. But be very careful. I just didn't add 3 squared on this side because it's inside a set of parentheses. I technically added twice of that. I'm bringing that in as extra. So that is the extra piece that I have to subtract off at the end to make sure that it stays equal and balanced. Okay? All right, the only difference now, we still have our trinomial squared. I just have this number out front. So I'm still going to keep the 2. I'm still going to throw an x in there. I'm still going to put a 3 in there. And I'm still going to put the first sign in there. And that is my quantity squared. I still have to also clean up this in the back. So this gives me a 10 minus, now 3 squared is 9 times 2 is 18. Looks like this is a minus 8. So therefore, y equals 2 times x plus 3 squared minus 8 gives me my final vertex form for that. Now, we've done it twice before. What is the vertex? Take the opposite of what's with the x, take this as is. Negative 3, negative 8 would be our vertex. Okay? All right, the last piece on this page that we need is our y-intercept. Now, here, remember, we let y equal 0. If I'm trying to find a y-intercept, I need to let x equal 0. Now, where is it? Can I put 0 in for x and find the y? Well, I have one form, I have two forms, and I actually have 3 forms. I actually have the standard form, and if I wanted to throw that in there, why not? I would put this into the original. So if you let x be 0, I'm really looking at what's the function at x equaling 0. That means, whoops, I do 2 times 0 squared plus 12 times 0 plus 10. Well, what happens on these first two terms? That's 0, that's 0. Plus 10 is 10. Therefore, my y-intercept is 10, but if they want it as an ordered pair, x was equal to 0, so it would be 0, 10 as the ordered pair for that intercept. Okay? So, the section is really, really heavy on some of these processes, but it is nice to be able to have those different forms so that you can end up working with different forms to find what you need. Sometimes it's easier on one versus the other. All right, let's look here. The last part of our section is solving quadratic equations with a formula. So, we found to solve those with the factored form to find our x-intercepts, but we're actually now going to use a formula to find our solutions of our equation, which are actually the x-intercepts. We also call them roots sometimes. Solutions, roots, zeros, x-intercepts, those are all the exact same thing. So, the solutions of a quadratic equation, the answers, the roots of the form f of x equals ax squared plus bx plus c, which is also what we refer to as standard form, with a, b, and c being a member of the real numbers. That's just a technicality thing there. Our formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, granted, I'm not the best singer whatsoever, but having a nice little tune for that to go along with is very important because it is a big formula and it is one that is important to know. So that makes it a little bit easier. So, again, no judgment on the singing part, but x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, to be able to do this, we must have our equation equal to 0 if we are finding the roots of our quadratic equation. So let's do this 3 times. We need to decide what a, b, and c are because all it is then is a formula, okay? So a is in front of the x squared, b is in front of the x, and c is the constant. Now notice, c here is negative. If it's negative, you better take the negative with you. If this one is positive and this one is positive, so make sure you take the negatives with you. All right, x equals the opposite of b, which would be a negative 9, plus or minus the square root of b squared, which is 81, minus 4 times a times c all over 2a. And those are our numbers plugged in. It is just a formula. Just like if you were doing the area of a rectangle or the perimeter of a rectangle. It is a formula that you just plug numbers in. So here we have to clean up what's inside that square root. So notice here, 4 times 2 is 8 times negative 5 is a negative 40. So really I get 81 minus a negative 40 inside there. And this double negative becomes a positive. 81 plus 40 is a 121 all over 4. Now, what the advantage of getting 121 is that it is actually a perfect square. What number times itself gives me 121? Well, that number is 11. And so you want to make sure that you break that down to its perfect square if it is at all possible. Now, this plus or minus is a shortcut way of saying one answer is negative 9 plus 11 all over 4, and the other answer is negative 9 minus 11 all over 4. And if you have a perfect square, you can actually break that down to where you actually find the two distinct numbers that make that true. So what is negative 9 plus 11? Well, that is 2. 2 over 4 is 2 fourths, which reduces to 1/2. Negative 9 minus 11 is negative 20. Divide by 4 is negative 5. Therefore, those two answers are my roots, or the x-intercepts for that polynomial. Okay, let's try another one. A is 2, B is 3, C is negative 1. We plug it into the formula. X equals negative B. So take the opposite of what you're looking at. Plus or minus the square root of B squared, which is 9, minus 4 times A times C, which is negative. So be very careful in there when you have a negative on A or C. All over 2A. All right. Simplify inside here. I get 9 minus negative 8. 9 minus negative 8. Double negative again gives me a 17. So negative 3 plus or minus the square root is 17 all over 4. And this time the 17 does not break down. 17 is a prime number. So you can't go any further than that. Okay? All right, very good. So, last one. A this time is a nice invisible 1. B is actually a negative 5. And C is a positive 5 here. So let's see what we get. If I do x equaling negative b, the opposite of b, so the opposite of that is a positive 5, plus or minus the square root of b squared. Now, be careful, if you do negative 5 squared, remember, anytime you square a negative, it becomes a positive. So that becomes 25 minus 4 times a times c. Be careful putting those into your calculator. All over 2a, so 2 times 1 is what's in the bottom. Now, again, caution, if you do negative 5 squared in your calculator, it will give you negative 25, which is wrong. You want to take the whole thing squared to get a positive 25, which is correct. Okay, so your calculator is only as smart as what you entered in to be. All right, let's clean this up. 5 plus or minus the square root. We get 25 minus 4 times 1 times 5 is 20. So 25 minus 20 gives me a 5 all over 2. And that would be the exact form. Now, if you don't know how to use your calculator, you probably want to make sure that you can use these to find a decimal value. So if you do 5 plus root 5 all over 2, make sure that you do like 5 plus root 5 hit equals, and then do the divide by 2. So one answer that you should get, and I want you to kind of check these to make sure that you get the right numbers. 3.62 would be 1 root, and 5 minus root 5 hit equals all over 2 ends up getting you, I'm trying to do it right now, 1.38 if you were to round that. So you might want to pause for a minute and double check so that you can get a decimal correctly on your calculator. If you have questions, please let me know. All right, our last piece here is an application of quadratics. The most widely used example for quadratics is a projectile motion type problem, because when you throw a ball in the air, what happens? It has this nice parabolic arc to it, okay? So here we have a ball that we are throwing from the top of a 40-foot building, and it is going to go up and it's going to come down, okay? So, the first question here, well, first off, it's at the top of a 40-foot building, we throw it at a speed of 80 feet per second, and the ball's height above ground can be modeled by this equation, where t is equal to time and h is equal to the height. When does the ball hit the ground? Well, if we're asking for when, we're looking for t. What does t equal when we hit the ground? Well, what's the h? If they want us to find t, they better give us h. Well, if we're talking about the ground level, in mathematics, it's always nice that we can designate our 0 point. So a lot of times our ground level, sea level, anything like that, we represent a height of 0. So that's what we're going to do here. We're going to find t when h equals 0. Now, I'm going to put 0 right in here. I'm actually going to flip-flop it a little bit and do negative 16t squared plus 80t plus 40 is equal to 0. If I could factor some of that stuff out, that would be really great. There's actually a common 8 within there that we could actually divide everything out by. And actually, there's a negative out front. So, because I have an equation, I can divide every single term here by negative 8, which is the common factor. And it reduces my equation down to 2t squared. This divided gives me minus 10t. This divided gives me negative 5, and that divided gives me a big fat goose egg. Now, if you were to go and try to factor this, you can't do it. It's not doable, okay? It won't be able to factor. We used to call those prime. Okay, now we can use the quadratic formula to actually get a value on there. So, I'm going to use the quadratic formula here with this equation to solve for t. So, t equals negative b gives me 10 plus or minus the square root of b squared, which is 100, minus 4 times a times c, all over 2a. Whoops, that's a 2. It'll eventually become a 4 here in a minute. All right, so if I clean this up inside, notice 2 times 4 is, 2 times 4 is 8, times a negative 5 is negative 40. 100 minus a negative 40 becomes a plus in there. So we get 10 plus or minus root 140 all over. There's the 4 I wanted. Now, if you actually do this in your calculator, this is not a perfect square. So we're going to have a decimal here. So if you do 10 plus root 140 all over 4, you get 5.458 rounded. If you do 10 minus root 140 all over 4, you get negative 0.458. And those are my 2 times for when the height equals 0. Now, when did we hit the ground? Well, notice there's a parabola here, but a parabola didn't finish, right? I end up kind of extending that out. Notice this is representing time. So this is seconds and this is seconds. Does this answer make sense? Can I have a negative amount of time? And the answer is no. That doesn't make sense, but hopefully in the picture it kind of makes sense that this is the t value at 0. The other one, this is the 5.458 that we need for our number of seconds. Okay, so on applications, make sure that you actually still remember to answer the final question that we have. Okay? All right, part B and our last question in this section. What is the maximum height of the ball? So I'm looking for how tall it is up here. Well, we know it's above 40 feet, okay? But how tall is it if I launch that at 80 feet per second? I want to know where that occurs. Well, where does the vertex occur in any parabola? If I have this parabola and I have kind of 2 intercepts here, the vertex is symmetric around those, so it has to be smack dab in the middle of those 2 intercepts. So if I need to find this height, I need to first find its t that is halfway between those intercepts. Well, anytime that you need the t value that's halfway in between there, or halfway of anything, there is something referred to as the average that will get us that. And so, the average of our t's average, let's say, we would take the negative 0.458, add the 5.458, and divide by 2. You add them up and divide by 2. So that's going to give me my halfway point, and it actually works out very nicely that that's 5 halves, or at 2.5. So this is at 2.5 seconds, at which our height is its maximum. Now, the question asks, what is the maximum height? So using our function, if I'm finding my h, then I better be given t. Well, we just found t. T was at that 2.5 seconds. So here we go. We need to find the height at 2.5 seconds by plugging in 2.5 wherever I see a t in that function. So I get negative 16 times 2.5 squared plus 80 times 2.5 plus 40. And if you were to multiply all those things out, we get negative 100 for the first term. We get a plus 200 for 80 times 2.5. And then I have to tag on that 40, which comes out to be 140 feet. And that is the maximum height of that projectile. Okay? So that is a very, very nice problem and a prime example of what we have with projectiles. And so this section is packed with a lot of stuff on those quadratics. So make sure that you can work with the factored form, the vertex form, the standard form. Also be able to do the completing the square and solving with a quadratic formula like what we just did here on this last page. So we will move on into section 3.3, which we will go bigger than powers of 2 and get into some more polynomial functions. Until next time.